Okay, well, let's begin. Let's recall what we did last time. Basically, we didn't do much. We defined the symplectic action. Let's recall the definition. Is it plus or minus? I think it's a minus. Well, it's minus in both places. Okay, now okay, well, let me briefly review the notation. L naught is the space of contractible loops. U is a map from the unit disk inside C, which extends X. What is HT? HT is basically a given family of functions on M. Does the notation make sense? Well, we calculated the tangent space and the derivative. The tangent space is the tangent space is not surprisingly the set of all the space, the vector space of all sections of the pullback of the tangent bundle along X. Another way to think about the tangent space is this. We take the space of all maps from R to the tangent space, the tangent bundle of M. Such that psi of t is psi t plus 1, So the map is one periodic, and secondly, psi p is inside T x of T m. Meaning psi of t belongs to the tangent space to x at to m at x of t. Okay, does this notation make sense? Now we want to calculate the differential. Well, we don't want to calculate it, we've already calculated it. And the answer we found last time was this. Basically, the differential is even if we have a map defined on something which is infinite dimensional, the differential is a map from the tangent space to R. So the differential is something comprehensible. We know what the tangent space is, so to calculate the differential we need to specify its value on every tangent vector. In other words, on every element of the tangent space. Well, let me take such an element, and the result is omega minus xt taken at x of t. Okay, so this is the first argument. The second argument is psi of t, and we integrate along the dt. Now, last time we checked that the signs match. So there is no, there aren't any problems with the signs. We checked it last time. Now, what is xt? Well, xt is the Hamiltonian vector field, which is determined by the symplectic form on M and the differentials of the family HT of functions. Okay. Is there any sugar in it? Yes, there is, but there's less than in the other drink. Anyway, does x lower t make sense? Well, okay, let me first try to say it, and then we'll see whether or not we need to write it. We have x, we start with ht. This is a family of functions. Well, each of those has a differential. But we also have the symplectic form, which gives us an isomorphism between the tangent space and cotangent space at every point. So starting from the form and the differential of ht, we can construct a vector field. And we denote it xt. And this is what people call the Hamiltonian vector field, which
still gradient also, because this vector field is tangent to level set. Simple game, but nice.
to the level sets of H.
It's not gradient, it's in some sense orthogonal to gradient.
Well, it's sort of a gradient, but it's symplectic, so it doesn't behave.
No.
Well,
Растет по градиенту, а это постоянно. Совсем другой.
ну, это симплектический градиент. Там все по-другому. Там все не как у людей.
Это шутка, а я не шучу.
Если бы форма была бы симметрическая, то это было бы градиент в буквальном смысле. Но форма не симметрическая, поэтому нет. Okay. Well, again, we want to specify the differential at psi, and here is the formula, which we checked last time. There are potential problems with the signs, but we sorted them out, and it looks like the signs are all right. Okay. Does this make sense? X dot denotes the derivative with respect to t. Okay. Now. Now we want to calculate the gradient of this action, and this time it will be a genuine gradient. But to do this, we need a metric, and a metric on L naught of m. Well, let's define a metric, and then we'll calculate the gradient. Okay, now I need to erase everything because the board is quite small. Okay, well, probably I will put the formula for the action somewhere, because we will use it well quite a few times, and then I'll erase the rest. Okay, now again there will be a few potential sign problems, so pay attention. Basically, we want to construct a kind of Morse theory for the function A on L naught. Obviously there is no straightforward analog of Morse theory in the infinite dimensional case, but sometimes when our action is nice enough, there is a way to construct Morse theory which is more or less parallel to the usual finite dimensional Morse theory. In particular, if you take a look at what Milner says in lectures on Morse theory in chapter 3, I think, he considers another function on the space of loops, and then it turns out that the Morse theory analog for this function is very similar to what happens for finite dimensional manifolds. Here we have the same space, or more or less the same space, but another function. And it turns out that there is a Morse theory for this function, but it's more complicated, and the analysis is more complicated, and well, this is what we are trying to understand. And well, if you recall what happened in the first few sessions, we did talk about, or you did talk about Morse, about finite dimensional Morse theory. And I was ill, so wasn't there. And one of the main ingredients in calculating the Morse complex was the gradient flow. Now we want to do the same for our action A. Well, so we need to calculate the gradient flow, and to do this we need a metric. Or, more precisely, we need a kind of a Riemannian metric on L naught of M, meaning we need a metric on each tangent space. Well, to do this, we start we start with a periodic family of compatible complex structures, and then we We define the metric using, we define a metric for every t using the complex structures and the symplectic form. Let's remember that here we put j in the second place. Now, before we calculate the gradient, what is the gradient? Let's try to remember what happens in the finite dimensional case. Suppose I have a function on a manifold and a metric. What is the gradient of the function with respect to this metric?
Scalar product with gradient should be derivative.
Yes. So the scalar product with the gradient, or the gradient, I don't know how to pronounce it correctly. Anyway, the gradient is a vector. Such that the scalar product with this vector is the same as the differential of the function. Okay. Well, by the way, I didn't define the metric. So this definition just gives me a metric for every t. This gives me a metric on M, but then so here this is bad notation. Anyway, instead of trying to write it down, what it says here makes sense for psi and eta inside some tangent space to M. Now we want to extend this to a metric on this space. And we use this expression. Okay. So the gradient of A, scalar product with psi, must be dA applied to psi. Well, we already know what dA applied to psi is. Let me check the signs. Метры, нет, значит, да, Т везде одна и та же, но она варьируется от 0 до единицы. Okay, so we have this expression. So now we want to calculate the gradient or the gradient. We use so on the one hand we have this expression. Does it make sense to everyone? Basically, I just wrote again what I wrote previously and erased afterwards. Okay, now we rewrite this part using this definition. Okay, so now, I just used the definition on the board. Well, now I use the definition of the metric, and the result is the integral from 0 to 1. Omega okay, now let's change this definition a little so that we have J in the first place and no J in the second place. Let's see. So my claim is that this result, this omega is by anti-symmetry, this is the same as omega jt minus eta psi. And this by symmetry is the same as eta psi. Okay, so if I put a minus here, I get omega, then I take jt applied to this expression. Oh, no. Jt applied to this expression, comma, psi dt. Okay. So the by comparing the two formulas, we sorry. Hold on. This is strange. I probably went too fast. Okay. Let me. Let me erase this part. So here I have the gradient. So let me write the gradient again. J. The gradient of A taken at the point T, comma, psi of T dt. Okay, now we have on the one hand something that we know or sort of know. On the other hand, we have what we want to calculate, jt. So we basically need to equate this and this, and then we get the gradient. So the answer is the gradient of A taken at a point T is well, jt. I need to invert it, but jt is an almost complex structure. So instead of inverting, I could just take minus, and I have another minus here. So the result is jt applied to this expression, x dot of t minus xt taken at x of t. Okay. Now, okay, does everyone agree with the signs? Because that's where problems are susceptible to occur, and in fact they do very often. Отец, проследи за знаками. Okay, well, let's see whether this agrees with Salomon's notes. Well, the first term does agree with what it says in the notes. Now the second term is a bit trickier. Okay, so okay, well, let's, yes, so the first term here agrees with the lecture notes, and the second one doesn't quite agree, but let's see whether or not they are in fact the same. Okay. I will keep this formula, and then I will try to rewrite it, and I will erase the rest. Okay, well, let's see. So what Salomon says is that xt taken at x of t is the same as the gradient of h t taken at x of t. The gradient with respect to which metric? Oh, no. Jd. The gradient with respect to h, no, with respect to the metric at t. Well, let's try to check this. Okay, now so what is the gradient with respect to the metric t? it's a vector such that we have this for all alpha inside T y of m. Okay, now we know that this expression is well. This expression is the same as omega. Which is the same omega jt ht alpha. Well, here we use the same trick as before. If we want, we could put j in the second place, or we could put it in the first place, but then we need to have a minus. Okay. Now let's recall the definition of xt. Omega of xt alpha is dht applied to alpha. Alpha again is an element of the tension space to M at some fixed point. Okay, but by the way, is it a plus or a minus here?
Depends on the author.
Depends on the author. Okay. Well, let's see what Solomon prefers. Okay. Well, he says IXH omega is the H. Which is brilliant because the problem is the same. What is do we substitute XH in the first place or in the second place?
The first one.
In the first place. Okay. So if we use this convention, then we have a plus here. Does everyone agree? Well, I substitute XH as the first argument, I get some linear function on the tangent space, blah blah blah, and this linear function should be dht. Okay, now okay, what happens if I take omega of GT HT alpha? My claim is the result is the same as minus omega HT alpha, HT J alpha. And here we use the fact that the almost complex structure is compatible with omega. Basically the same trick as we used here. And the result is the same as
What is HT?
HT is one of the periodic family of functions which is part of our data. We're given HT. It's a function on M. For every fixed t, we have a function on M.
So it's an operator.
Sorry. Yes, it does. It doesn't. Sorry. Yes. Yes. Thank you. It doesn't make sense because yes, it's supposed to be HT. So the result is minus dHT applied to JT alpha. Let's look at those expressions and see whether or not they coincide. So we want to prove that this vector is equal this vector. Let me look again at everything I wrote, and then maybe it's already there. Okay, so this is the definition of This is the definition of xt. Okay. Let me rewrite this as x t alpha with a minus at t. Так, ну все, что-то я запутался. Сейчас, значит, okay, all formulas are there, but let's see why they give the same result.
С точностью до знака получается.
Ну, сейчас.
Вот туда написать перед альфа почти комплексный оператор.
Да, значит, так, значит, здесь у нас получается значение дифференциала в точке g альфа, но мы сейчас его, наверное, переправим. Да, значит, здесь значит, минус дифференциал в точке значит, g альфа, здесь плюс дифференциал в точке альфа. Значит, спрашивается, почему, с какой стати это одно и то же.
Мы хотим доказать.
Значит, мы хотим доказать, что значит, левая и правая часть совпадают.
Да, мы еще перед x получается
Где? В общем, оно, скорее всего, следует уже из того, что написано, но поскольку написано все там, хаотически, как оно следует, не понимаю. Но давайте чуть подумаем. Well, here is the definition of xt. By the way, is there another same problem? No, it looks like. Okay, so this is the definition of xt. Okay. Now, omega of this is equal to this is equal to this. Let's try to
we can replace alpha by JT alpha on the main disk.
Yes, but this, but then this.
Что мы сейчас хотим доказать, что сейчас?
Мы хотим,
Написано сверху.
да, мы хотим доказать то, рядом с чем написан вопросительный знак. Ну, тогда формула сойдется, значит, с той, которая у Соломона. Пока она похожа, но не совсем идентична. Okay, so we.
А сейчас она отличается знаком при H. Да?
Нет, а сейчас она еще отличается тем, что в одном случае при альфа есть J, а в другом случае нет J.
В двух местах нету, нет. Нет, там главный член, это вот GT от U с точкой. Вот это самый главный член. Ну, сверху он есть. Сам первый.
Это X точка.
Ну, не важно. Вот это главный член.
Да, значит, да, значит, главный член сходится, остались детали. Вот.
Маленький добавок,
Вот,
там
да.
знак может быть любой.
Подожди, там, значит, нет, там сейчас, подожди, ну, здесь, сейчас, давайте чуть подумаем, здесь, значит, скорее,
Мы можем вместо альфа там написать JT альфа, тогда слева заменится на JT альфа. Вот. Вроде бы. То есть вот нижнее, что там написано, будет равно тому, получается.
значит, так, значит, ну да, мы можем написать везде, значит, GT альфа, значит, тогда там какие-то части совпадут, но здесь, значит, здесь у нас, именно скалярное произведение xt с альфой.
Это не скалярное произведение.
Ну, минус скалярное
Ну,
произведение.
хорошо, скалярное. Ну, тогда мы там сможем перекинуть на... А нужна такая... Сейчас, можно я нарисую?
Нарисуйте.
Сейчас, подожди.
Нет.
Сейчас вот я добавлю сюда минус GT. тогда у нас здесь убраться.
Да.
Вот. Тогда у нас есть такое выражение, то есть вот это тождественное, это равно этому. Значит, у нас получается что такое минус равно минус равно. Вот, это можно сюда.
Так, сейчас. Так, хорошо. Это значит здесь у вас что, минус или плюс?
Нет, вот минус вот здесь.
Так, хорошо.
Вот. Теперь хочется JT сюда перекинуть.
А это можно сделать, потому что
Ну, значит, JT, он, значит, он,
банальный оператор для этой метрики.
нет, он не только ортогональный, он еще и антисимметрический. Он такой по совместительству.
Но сейчас нам важно то, что он ортогональный.
Значит, ну, ортогонально это значит, что мы можем перекинуть, и он станет обратным.
Да.
Антисимметрически это означает, что мы можем перекинуть, и он станет минусом.
Да.
Значит, ну и тогда, значит, что получится?
Сейчас. Ну, то есть...
Значит, получится, значит, JT градиент омеги T.
Да. Вот так.
Значит, равняется минус xt.
Да. Вот. И еще раз можем изменить к обоим частям JT.
Так, да, значит, умножим теперь обе части на минус JT. Слушайте, сошлось, действительно.
Верно.
Да, значит, что произошло? Мы значит, взяли какие-то формулы, про которые мы знаем, что они верны, потом стали их случайно подставлять, значит, случайным образом друг друга. И вот там в результате таких многочисленных постановок, значит, мы получили, что правая часть равна левой части. Вот, значит, да, но при этом вот эта вот хаотичность постановок, она немножко, значит, немножко не нравится, но что выросло, то выросло. Anyway, after randomly substituting formulas into other formulas, we sort of prove that this formula is true. Why sort of proved? Well, because there were quite a few false attempts and a bit of trial and error, and basically there is a cleaner way to prove this, which I suggest we leave as an exercise.
Я думаю, что время до перерыва как раз то, потому что нас в любом случае...
Да, но сейчас нас сюда выгнет. Okay, well, but first of all, let's take a look at this formula. Does everyone agree?
Which one?
Well, basically this formula and the proof on the blackboard.
The first line is...
Well, the first line is no. The first line is something we proved, and Salomon gives a different expression, but we've just proved that those two coincide. Okay. As I said in the beginning, the analysis in the symplectic case is a bit more messy than in the orthogonal case. I don't have a philosophical explanation. Just happens to be so. Ну, в симплектическом случае в теории Морса, значит, аналитические детали сложнее, чем в ортогональном.
Пока что нет.
Значит, ну, что значит, ну, я бы сказал, что, ну, значит, уже мы и так видели, значит, часть безобразия и. Okay, well, let's. Is it on? Yes, the microphone is on. So what happened? What happened just now during the first half? We have calculated the gradient of A, and the answer is. Well, there were two answers. One is this, and the other one is T x dot T minus minus the gradient of ht calculated with respect to the metric at the moment t. Okay. Now, if we have the gradient, we have the gradient flow. Of A, what is it? I will write the formula first, and then I'll explain what the formula means. Sorry, there's something is. There shouldn't be any brackets here. Okay, where so we have an equation. An equation. Let me write here the derivative of u with respect to t. Minus the well, the gradient of ht calculated at u of st. Well, basically, we want to construct a family of maps from a family meaning a family of maps from the circle to M, which depends on another parameter S in R, and we want the partial derivative of u with respect to S to be the gradient of A calculated at the restriction of u to the circle given by S equals some constant. There it is.
May I ask a question?
Well, yeah, you may, but I may or may not be able to answer.
Yeah. Do we understand what is the critical points of A? Of functional A?
Well, let's have a look at this equation. Well, the critical points are the points where the gradient is 0.
Yeah. But how they connected with
we basically, well, the critical points are functions from the circle to M, such that we have this. Now,
such that we have this is equal to 0.
yes, this equal to 0. Now, the resulting equation is something that was probably already mentioned in this class at some point. Well, critical points of A. It's x from R by Z to M, such that jt x prime of t minus well, calculated at x of t minus the gradient of ht is 0, and this is something we that was already mentioned probably in the first or second meeting. Now, what is this equation? Well, basically, JT is an invertible matrix. So, equivalently, we could write this equation as h prime x prime of t equal xt. Well, again, and these two are equivalent. Okay, what does this equation mean? I don't know, but this equation is so this is the equation that we want to calculate the periodic solutions of. Our goal, Arnold's conjecture, and so on and so forth, is about the number of, or giving a lower bound for the number of periodic solutions of this equation. So the resulting equation is related to the critical points of the gradient function are precisely the periodic solutions of that we're looking for, that we want to estimate. Do you agree? Okay. Well, let's see. So we have the gradient flow. What does it have to do with periodic solutions? Under some assumptions, finite energy, a solution of this equation will converge to a periodic solution of this equation when t goes to plus or minus infinity. Well, yes, when s get, well, t is inside the circle. It doesn't really go to infinity. Yes, so we want to explain all this. And, well, in particular, what is energy and how is it related to this equation? Well, let me define the energy. Energy is supposed to be energetic, so I'll use the red pencil. Energy of what? Of a function u from well, from R cross the circle to R. No, not to R, to M. So suppose I have a function, a map from R cross R by Z to M, and I want to define the energy. Well, I simply integrate well, I take the modulus of the modulus of this, and squared the modulus of this squared. Well, since I have JT here, I forget the modulus. I just write du by dt minus or plus, which one is it? Minus, I think, x t squared ds dt. Okay, now the question is, I take the square of the modulus of something. Well, where does this something live? Du by ds, du by dt, and xt. Where do they all live? Well, they live in some tangent spaces. Tangent spaces have metrics, many of them. Which one do we choose? And I've thought a bit about it, and I think the answer is it doesn't matter. Alternatively, we could, for example, use the metric that we have on every tangent space for every t from 0 to 1. Or we could just choose an arbitrary metric and use it. Doesn't really matter. What do you think?
Пробовали.
Такое ощущение, что здесь написан норма, в какой метрике, все равно в какой.
Потому что мы наковыряли все метрики.
По крайней мере, значит, я не понял, там, какой смысл брать вот именно ту метрику или те метрики, которые у нас были. В общем, здесь, по-моему, не важно. Okay, so let's just let's just say that we do not make any assumptions on the metric on TM. Just take any metric. And now we want to prove a proposition. Complicated proposition, which we will partly prove today, and maybe prove the rest at some other point. So suppose we have suppose I have suppose I have a solution of one of these equations. Then the following the following are equivalent. Oh, and by the way, I call this expression E of u, and it may happen that E of u is infinite. Why not? Because we integrate from minus infinity to plus infinity, the result may well be infinite. But then it may happen that the result is finite. And the assumption that E of u is finite is equivalent to a few other things. Let me. So the other statement equivalent, another statement equivalent to this one is that the fact that there exists a limit, a uniform limit of u, uniform in t, when s goes to plus minus infinity, and these are periodic solutions of one periodic. Of this equation. And finally, the third statement is that the s derivative of u decreases very fast namely it decreases exponentially when t goes to when s goes to infinity. Or actually, another way to say it would be to put a constant c here, and require that this constant should be positive, and and then we can include all st without further conditions on them. Okay, now this is the reason. This is the reason we are interested in solutions of this equation, which have finite energy. Okay, now, there are three implications. Salomon says that 3 implies 1 is obvious. Well, let's see. Let's not argue whether or not it's obvious. Why is it true? Let's recall that u is not just any function, it's a solution of this equation, or of this equation, or equivalently of du by ds plus jt du by dt minus xt. Yes, if the first part du by ds is very small, then so is jt times the second part, and then the integral exists. Maybe here we. It would be more convenient to use the metric we constructed using the symplectic form, because then jt becomes an orthogonal operator. Although I think it really doesn't matter; it would work for any metric. Okay, and basically the both sides are bounded above by the integral of minus the exponential, which is finite. Володя, имеет ли это все хоть малейший смысл? Так, ну то есть смотрите, вот значит, у нас есть что? Да, у нас есть вот u, который удовлетворяет уравнению. Вот у нас, значит, мы предполагаем, мы хотим доказать, что из 3 следует 1. Значит, мы предполагаем, что производная по S очень маленькая. Вот, но так производная по S очень маленькая, значит, соответственно, то, что там вот другое слагаемое в уравнении тоже очень маленькое. Ну вот давайте сейчас, там, если мы хотим, давайте использовать значит, метрику в момент t, тогда значит, j и t становится ортогональным оператором. Ну там минус, ну, в общем, если мы применяем ортогональный оператор к чему-то маленькому, то мы получаем что-то маленькое.
И наоборот.
Значит, да, и наоборот. Теперь, значит, ну, а что нам нужно здесь просуммировать? Нам нужно просуммировать что-то маленькое и что-то еще маленькое. Ну, значит, это ограничено сверху, это экспоненты от минус s. Значит, это, ну, значит, тоже экспоненты от минус s. Ну, соответственно, значит, интеграл сходится. Okay. So, well, this implication is indeed quite straightforward. Well, let's prove the another implication. Let's prove that 1 implies 2.
Оставь формулу для интеграла.
Я сейчас где-нибудь на другом месте напишу. Так, здесь видно? Нет, уже почти ничего нет. Так. Okay, well, this is the formula for the energy. Where xt is calculated at u as t. Okay, so let's try to prove that 2 implies, no, 1 implies 2. And then 2 implies 3 will hopefully be proved later. Okay, now here there is a point in the proof which which I don't understand, and there is another point which which I sort of understand, but not not the way it's written in the note. So please pay attention. First of all, Salomon suggests we use the following a priori estimate. Now I will write it down, but I don't know how to prove it. Namely, suppose I have a solution of the gradient flow equation. Then if the integral of du by ds squared along the ball of radius r in the st plane is less than h, moreover less than h bar, the Planck constant. I don't know what it has to do with anything, but anyway. So if this integral is less than h, then and here we have s and t, which are fixed. So we fix s, t, and r, and we suppose that this, by the way, here we integrate dr, ds, dt. Okay, ds, dt. Okay, so well, it's bad notation. Let me put a 0 here as naught t naught. So if this is less than h, then the value of the second derivative squared is less than or equal 8 by pi r squared, the integral br, well, the same ball. And this time we integrate by the way, if we know how to, anyway, I'll just write it down, and then we'll use it. And well, I sort of understand how one could try to prove this, but plus CR for some R greater than 0, C greater than 0. Okay, well, let's have a look at this again. What does the estimates say? It says that if we have if we have a solution of this equation, the gradient flow equation, then if the integral of du by ds is small enough, then the value, the integral along a ball of radius r centered at S0 T0. Then the value at the same point S0 T0 can be estimated using this this formula. Сейчас я переписал буквально.
Я согласен. И я просто не понимаю, там вот мы делим на r квадрат, а r у нас как бы маленькая, нет?
Нет, r произвольная. Значит, мы r берем r берем в плоскости st.
Да, да.
Не обязательно маленькую, может быть, это может какую угодно.
Ну что мы хотим доказать? Правильно ли, что мы хотим доказать, что какая-то частная производная, вот эта по S, маленькая?
Да, мы хотим доказать, что частная производная по S, но уже не ее интеграл, а значение частной производной маленькое.
Но если ты говоришь, что R большое, то
нет,
ничего не получится.
значит, ну, маленькое в том смысле, что вот это вот больше или равно ее.
Мы хотим доказать, что вот это то, что слева маленькое, ну вот это, я правильно понимаю? ду ПДС должно стремиться к нулю на концах, если мы сходимся.
Значит, ду ПДС должно стремиться, значит, ду ПДС должно стремиться к нулю, правильно.
Равномерно.
Значит, но нет, значит, там, нет, значит, мы знаем, что интеграл, значит, dr, значит, от там, у ПДС в квадрате сходится.
Да.
Значит, что это значит? Это значит, что интеграл от вот этого вот, значит, по шарам, которые там лежат в области S достаточно большое, по любым шарам, вот, там в этой области, он будет маленьким. Вот это мы знаем.
Меньше любого числа становится.
Да.
А R, поэтому нам не важно.
Значит, R не важно, если оно остается внутри того же шара.
А вот эта C, она равномерна, ну то есть
C константа.
какая-то вообще константа.
Да, она, да, не, да, она не, значит, сейчас, она, по-моему, сейчас зависит ли она от U, давай посмотрим. Значит, C не зависит от U, и H тоже не зависит от U.
Ну, U зафиксировано у нас, поэтому...
Нет, вот понимаешь, здесь, значит, во-первых, я не знаю доказательства, поэтому значит, уверенным быть нельзя. Значит, но что происходит? Значит, вот как я понимаю то, что сказано, значит, вот это вот импликация, здесь импликация, значит, верна, импликация верна для констант, значит, H и C, которые не зависят от U вообще никак. Значит, но если мы предполагаем, что U решение, значит, решение вот этого уравнения. Вот теперь, значит, а как это все доказать? Ну вот, значит, у меня такая идея, что нужно вспомнить, значит, формулу, значит, которая доказывает, что средняя гармоническая функция – это там по шару, значение в точке. Есть такая формула, она, там ее очень любят там, в этих там частных производных и так далее. Значит, вот, значит, пусть у нас есть, значит, какая-то функция, там, n переменных, значит, гармоническая. То есть Лаплас, обычный самый Лаплас равен нулю. Тогда утверждается, что средняя функция по шару равно значению в центре, а также, значит, средняя функция по сфере равно значению тоже в центре. Вот, ну, там одно следует из другого. Значит, вот если поиграть немножко с этими, значит, формулами, которые там доказательства, наверное, вот можно вывести вот это, но я не смог. Okay, so let's assume this, that this implication is true and see whether or not it helps. Okay, so well, the first step is to say that if the energy is finite, then okay. So let me write something down, and then we'll see whether or not it's true. If the energy is finite, then du by ds converges uniformly as s goes to plus or minus infinity. Let's see how to prove this. Basically, the problem is all we know is that the integrals of u over various balls become small, but we want the value, not the integral, to become small. And we all know that there are examples of convergent integrals from minus infinity to plus infinity. But the function itself may be unbounded and doesn't need to converge to zero, and so on. So this is the sort of phenomena we want to avoid. So let's prove this implication. And the proof is as follows. We choose an epsilon greater than 0, such that epsilon squared is less than h bar, but otherwise arbitrary. And we choose a t, again greater than 0, such that the integral such that the integral of what? The integral of, let me call this star, the integral of star along this subset is sufficiently small, which is possible because the integral converges. Okay, now okay, now we want to apply this mysterious implication. What do we need? What else do we need? Let's take r equal the square root of epsilon. Okay, then the first thing we want to check is okay. Now hold on. Okay, suppose now suppose. The modulus of S is greater than T. I probably need to make another assumption to make sure that the ball of radius r remains in okay, the radius r. Okay. Okay, I want to put something here so that t minus something is let me just put the square root of epsilon, because I want basically to be able to claim that this okay, I choose S naught T naught such that S naught is sufficiently large. Then the integral well, the first integral will be, well, it will be less than epsilon. No, it will be less than epsilon squared. And so it will be less than h. Okay, so I choose S0 T0 such that blah blah blah. Then the first integral is less than epsilon squared, and then I can estimate the second the value of the derivative du by ds S0 T0 well, will be what? Will be less than or equal 8 by p r squared, and well, I know that this integral, I know already that this integral is less than epsilon squared, less than or equal, plus cr squared. Okay, let's remember, r squared is epsilon. So this is the same as 8 divided by pi epsilon, and plus c epsilon, which is epsilon by 8 by pi plus c. And this is small. Well, if all this looks a bit messy and arbitrary, don't worry. It's analysis, and well, this is well, same as everything. This takes some getting used to. Отец, проверь, ну, там, в общем, в таких рассуждениях просто допустить ошибку.
Нет. По модулю самого первого
Да,
правильно.
да, окей. Okay.
Мне так кажется, то есть.
So the claim we're making is the following thing. We're claiming the following thing. As t goes to plus or minus infinity, as s goes to plus or minus infinity, the derivative with respect to s tends to, the derivative of u with respect to s tends to 0, uniformly in t. Yes. So what it says here is a bit confusing. So this argument not only shows that the limit exists, it also shows that the limit is 0. Ну вот, значит, вот это анализ, там, допустим, там, если вы пришли из геометрии топологии, вот эти все, значит, эпсилоны, которые равны там корню квадратному, они кажутся дикостью. Вот, но нужно не забывать, что в другую сторону, значит, в другую сторону тоже, значит, тоже верно. Когда, значит, аналитик пытается выучить топологию, значит, вот эти вот рассуждения, что там что-то стянем, потянем, они, значит, тоже кажутся какой-то дикостью. Вот, ну, вот немножко разные области, соответственно, там, значит, разный способ думать, значит, и, в принципе, там, ну, имеет смысл там, в какой-то степени, значит, овладеть этой техникой тоже. Okay, now, what else? Yeah, so we have proved this. The u by the x has a uniform limit, but then so does the right-hand side of the equation, namely du by dt minus xt. Calculated at ust. Meaning this thing also tends to 0 when t goes to, or s goes to plus or minus infinity. Okay. Okay. Well, we've run over time, but I suggest let's finish the proof, and then we'll see, and then we'll do something else. Do something else next time, because if we don't finish the proof, we'll never. If we don't finish the proof now, we'll never finish it. What do you think? If you need to go somewhere, please let me know. Okay, let's finish the proof. Now here. Okay, lemma. For all epsilon, the greater than 0, there exists a t greater than 0, such that if the modulus of S is sufficiently large, then then UST belongs to the epsilon neighborhood of some periodic solution of the equation that we want to that we are mainly interested in. Okay, so the epsilon neighborhood in the uniform sense. Uniform in T. And so for every epsilon there exists a T greater than 0 and so on. So this is the lemma. Let's first see why this lemma helps. Well, suppose we prove the lemma. Now, then well, basically, we probably need to make some assumption, or maybe we've already made this assumption, but I just don't know it. We need the solutions to be we need this set of periodic solutions to be finite, or at least discrete. Because, oh, by the way, well, if it's not discrete, then we've proved Arnold's conjecture, so nothing to worry about. Because if we have infinitely many periodic solutions, then well, Arnold's conjecture is true, because the sum of the Betti numbers is finite. Well, victory. So let's assume that there are finitely many periodic solutions. Then, if I choose T large enough, the function UST as a function, and if I choose T, capital T, not small t, capital T large enough, and fix S greater than this T, then this thing will be in the epsilon neighborhood of just one periodic solution. Why? Because there are finitely many, so the set of all periodic solutions with respect to the uniform metric is Hausdorff. So when I choose epsilon small enough, I get just one periodic solution instead of some periodic solution here. What could happen is that for S equal 1000 I get one periodic solution, for S equal 1 million I get another one, and U will converge to neither. But it doesn't happen. Do you agree? Okay. So, this lemma implies what we're after, at least in the case when there are finitely many periodic solutions. Okay, now we need to prove the lemma, and there is a hint in the notes, and I don't know how to use it. But I have a very similar argument, which I think works. So let me. I don't want to erase anything because then it's easy to lose track of what we want to do. Let's try to prove the lemma. Does everyone remember the Arcelor-Ascoli theorem? Let's see. Suppose we have a compact metric space. It's a useful theorem. Suppose we have a compact metric space and some family of functions from this space to R. Let me call it K. K is compact. If and only if the family is uniformly bounded, which means there is some constant greater than or equal every fi. And I've forgotten the name for the second condition in English, so I'll just look it up. Равностепенно непрерывная, да, вот, к сожалению, по-английски я не каждый день употребляю это слово, поэтому uniformly equicontinuous. What does this mean? This means all maps from X to R are uniformly continuous. This is a theorem by Cantor or Weierstrass. Probably Weierstrass. I'm not sure. And what does what does uniformly continuous mean? Well, it means that if for every epsilon there exists a delta such that if 2 points in X are delta close, then their images in R are epsilon close. And equicontinuous means the same thing, except that we can choose the same delta for which would work for all elements of the family. Well, okay, so we have this, and and the first condition is straightforward, and the second one is less straightforward, but if x is well, in our case, x will be what? We'll shortly want to apply this to well, in our case, x will be S1. So if X is a smooth manifold, all Fi are I think C1 would suffice. Then the second condition is equivalent to then the second condition is equivalent to requiring that the first derivatives of Fi should be uniformly bounded. Do you agree?
Yes.
And well, this is easier to check than uniform equicontinuity from scratch. Okay. Well, in our case, S will be the circle. Well, let's see. So this is the Artsela-Ascoli theorem, and it's probably in the functional analysis course, or maybe in the calculus course for the first or second year. I don't know. Okay. Well, let's use this. This theorem. What do we want to prove? We want to prove that we want to prove the lemma. Так, по-моему, уже никто не следит. Так, значит, хорошо, сейчас, значит, нет, если уже все, значит, силы закончились, то, ну, давайте докажем лемму, значит, в следующий раз. Okay, but then, well, we'll need to, okay, we'll need to recall, well, we'll need to recall something. Okay, am I right that nobody is really following? Are you following or are you not?
Ну, отслеживаю в целом, да. Так, говорю, тяжело мне немного.
Так, хорошо. Значит, в общем, повторение мать учить. Вот, давайте, значит, следующий раз, значит, докажем эту лемму. Хорошо. Well, let's prove the lemma next time. In which case, are there any questions?
Это лемма для чего?
Мы только что из нее вывели, значит, то, что нам нужно. Are there any questions? Okay, well, let's call it a day and stop the recording.